Okay. The last thing we look at in our study of the properties of limits is the squeeze theorem. This is a very good theorem that will be used to solve a couple of problems on limits. Our essential question is, what is the squeeze theorem and of what use is it? Remember, the squeeze theorem can also be called the sandwich theorem. In some books, you may see it written as a sandwich theorem instead of the squeeze theorem. But both words are okay to use. So, before we get into the squeeze theorem, I just want to illustrate. Let's say you have two functions, f of x. For instance, you have a function like this, f of x, and you have another function, g of x. G's of x. We can see here that if there is a point here, A, near the point A, f of x is always less than g's of x. No, f of x is always greater than g's of x. In other words, g's of x is less than or equal to f of x. And if g of x is less than f of x near A, it means that the limit as x approaches A of g of x will also be less than or equal to the limit as x approaches A of f of x. In other words, as you can see, close to A, the value of g of x is going to be always smaller than the value of f of x. What we are saying is that at this point, close to this point A, we can hold these functions together and squeeze them together. That's the word squeeze. Squeeze the functions. Squeeze the functions. The functions f of x and g's of x together. If we squeeze f of x and g of x together at that point, then our f of x and g of x will look something like this. This is, say, your f of x, and this will be, say, your g of x, and this is your f of x. So we have squeezed the functions together at the point x equal a. And as we have squeezed them together, you now see that the limit is the same at those 2 points, right? So we still, so for this case, the limit as x approaches a of f of x is equal to the limit as x approaches a of g of x, which is some value L. Now, what does the squeeze theorem say? The squeeze theorem is trying to use the idea of squeezing those functions. If we have our f of x like that, and we have our g of x like that, such that the limit as x approaches a of f of x and g of x is the same, but g of x is always less than f of x. You can see near a, g of x is less than or equal to f of x. And if we have another function, let's say another function is in between these two functions. Let's call that function h of x. If h of x should always be in between f and g, then the limit of h of x as x approaches a must also be equal to L. Right? So that's the squeeze theorem. It says that if f of x if you have two functions, g of x less than or equal to f of x, and you have a third function, f of x, in between them. So, in other words, you have g of x is less than or equal to h of x, and less than or equal to f of x near a. So, if you have this, and if the limit as x approaches a of g of x is equal to the limit as x approaches a of f of x equal to L, if the limit of this function as x approaches a equal the limit of this function as x approaches a equal this value L, it means that the limit of the function that is in between them, the limit of h, it means the limit of h should also be equal to L. So if this, then the limit as x approaches a of h of x should also be equal to L. So that is the squeeze theorem. We can use an example how the squeeze theorem would be useful. We want to find the limit as x approaches 0 of x squared sine 1 over x. We know that sine of 1 over x will lie between 1 and negative 1. The sine of any value of x will be from negative 1 to 1. We can now multiply this whole expression by x squared. This means that negative x squared will be less than or equal to x squared sine 1 over x less than or equal to x squared. Now you see that the middle function is the limit that we are looking for here. So we can now take the limit of all of these sides. We see here that the limit as x approaches 0 of negative x squared is the same as the limit as x approaches 0 of x squared, and this limit is equal to 0. Therefore, by the squeeze theorem, the limit as x approaches 0 of the middle function, which is x squared sine 1 over x, must also be equal to 0. Why? Because the limit of this equals the limit of that, which is 0, and this function is between those two functions. So how does it look like? We can draw, if we draw the graph of y equal negative x squared, y equal x squared, and y equal x squared sine 1 over x, we'll have something like this function. You see here, this is y equal x squared. And here is y equal negative x squared. And if we draw the graph of y equal x squared sine 1 over x, we'll see that it is always between x squared and negative x squared. And because the functions are squeezed at this point, the value of their limits should be the same. Remember, if you have to draw these graphs on your calculator, use the correct viewing rectangle. Otherwise, you will not see the function as it is. Okay, that is it. Please solve exercise 71 to 76 on page 68. Thank you.